Okay, very good morning, Dr. Nitesh Kashyap, sir. Very good morning, sir.
Good morning. Good morning,
Okay,
Dr.
shall we start now, sir? If you
Yes, sir.
allow.
Sure, sure.
Okay, thank you very much, sir. So, very good morning to everyone. I greet all of you on the behalf of NIT Jalandhar in the fourth day of this short-term course. So, it's a great pleasure for me to introduce our speaker for today's morning session, Dr. Nitesh Kashyap, who is going to share knowledge with us about the spiral antenna design. Before starting the session, I want to give you the brief introduction of today's speaker. So, Dr. Nitesh Kashyap has received Bachelor of Engineering in Electronics and Communication from Jivaji University, Gwalior, and Master of Electronics degree in Microwave Engineering from Jabalpur Engineering College. He has completed PhD from IIIT TDM Jabalpur in December 2016. He has visited Loughborough University, London for research. He is the member of several international technical societies. Currently, he is working as an assistant professor at NIT Jalandhar. His main research interests are microwave component, broadband antenna, high gain antenna, and circularly polarized antenna design. So this is, and we are the short of time, and already we are 10 minutes late. So I think we should start now. So I call upon the today's expert, Dr. Nitesh Kashyap. Sir, it's
Thank you. Thank you, Dr. Manjeet.
thank you very much. You're welcome.
Thank you. Good morning, all the candidates and faculty. So, is my screen is visible? My screen visible?
Sir, it's visible, sir.
It's visible. Okay.
Yeah.
So, just a minute. Okay. So, okay. Okay. Now it is visible?
Yes, sir, it's visible.
Okay. Thank you. Okay. Thank you, Dr. Manjeet. And I am Dr. Nitesh Kashyap from NIT Jalandhar, and I am going to present uh, the spiral antenna design here in this session. So, especially that when we talk about the antenna, uh, everybody heard about the antenna. So I will share the story of antenna here. So now this is my outline of the presentation. I will I will present the introduction, then history of antenna, and transmitter antenna, receiver antenna, and so on. So yeah, that is we were talking about antenna. So the antenna is nothing but just a transducer which converts the guided wave into the free space wave. So when we talk about the antenna, we cannot uh, assume any wireless communication system without antenna. I think you may agree with me. So right now, in today's era, that we have seen several antenna around us, that I have shown some antennas here, like that dish antenna and the TV reception antenna, the dish TV antenna and the mobile antenna and the smartwatch, everything, whatever we are using right now, from morning to night, every wireless system has antenna. Even though the antenna is not visible in that device, but it is there. So antenna is the very integrated part of our daily life right now, because we are dealing with several wireless communication in our daily life. So the importance of the antenna and the antenna designing and antenna engineering is very important for the today's system or today's wireless communication system. So this is the brief history of the antenna. That antenna, the first antenna was made by the Heinrich Hertz in 1888, and he proved the Maxwell theory in the realistic manner. He transmits the electromagnetic waves from one end to another end. So, here that we can see that without transmitter and receiver, we cannot establish the radio wavelength, and the antenna is the most important part of the wireless communication system here. So without antenna, we cannot transmit the wave or transmit signal towards the receiver. So here, what is the transmitter stand for? That a device that converts sounds, light, and electrical signal into the radio, microwave, or other electrical signal towards the receiver. And what is the receiver stand for? That an real antenna is receiving something, or receiving electromagnetic wave to convert into the electrical energy, basically. So the basic structure of the antenna, I can say that here, that basic structure of the antenna contains the metallic structure, that it may be parabolic reflector, horn, and parasitic elements, and the antenna can be designed to transmit or receive radio waves in all direction equally. It is omnidirectional antenna. I will tell you what is omnidirectional antenna further. So, on the transmit them in a beam in a particular direction, it can be directional antenna. So what is the need of antenna? As I told you already, that need of antenna arises when the two persons wanted to communicate between them when separated by some distance, and wired communication is not possible. So first thing is this. Second is, antenna are required by any radio receiver or transmitter to couple its electrical connection to the electromagnetic field. Okay, and the third one is that radio waves are electromagnetic waves which carry signal through the air at the speed of light with almost no transmission loss. So there are technical specifications, but that we know that why the antenna we use. So the radio transmitter and receivers are used to convey signal in the in systems including broadcast radio, television, mobile telephone, point-to-point communication links, and satellite links. Radio waves are also used directly for measurements in technology including radar, GPS, and radio astronomy. These are some applications of the antenna that we need antenna for communication, in which in each and every case the transmitter and receiver involved require antennas, although these are sometimes hidden, such as the antenna inside an AM radio or inside a laptop computer equipped with Wi-Fi. So that are some points that I have written here, that for the antenna is very important or integral part of the wireless communication system. So where we can use the antenna. The antenna we can use in the radar systems and space exploration and wireless LAN, television broadcasting, point-to-point radio communication. So everywhere we use the antenna. Antennas are most utilized in air or outer space, but can also be operated underwater or even through soil and rock at a certain frequency for short distance. So there are some applications where we use the antenna in underwater or under soil. One example is that GPR, ground penetrating radar, where we use this antenna for the disaster management. So here, without parameter, without parameter of the antenna, we cannot evaluate our antenna performance. So there are some parameters. So as here, that radiation pattern can be in three types basically. The first is isotropic antenna. It is basically hypothetical concept in which a point source we consider and it radiates equally in a spherical manner. And second one is the omnidirectional antenna, where we can consider a dipole and it radiates in a plane. It can be XY plane or any plane. And the third one is directional antenna. It radiates in a single direction. Other than that, we have bidirectional antenna, so that can radiate in two directions. The second parameter is gain. The gain is basically where the radiated power we divide with the input power. And third one is polarization, directivity, efficiency, and impedance bandwidth. I will explain one by one them that antenna parameters. In the antenna parameters, the radiation pattern and radiation intensity are correlated. So the radiation pattern of the antenna is a representation, basically the mathematical or pictorial view of the distribution of the power outflow from the antenna or inflowing to the antenna as a function of direction angle from the antenna. So that radiation pattern tells us the how the antenna radiates, how it will react after the fading of the antenna. The radiation intensity is measure of the ability of an antenna to concentrate a radiated power in a particular direction. So we measure this radiation intensity in the steradian or solid angle. Second one is the beam width. The radiation pattern has have some certain characteristics, like that how the power is concentrated in the beam of the antenna. So we can evaluate or we can find the distance of the antenna where we can place the receiver antenna after the measurement of far field or after the measurement of radiation pattern where we can where the antenna is actually radiating. So that beam width is the beam width is key function or key characteristic of the radiation pattern here. So I can, you may see the antenna radiation pattern has some characteristic like main lobe, and that half power beam width, and the beam width with first null. So that main lobe has the almost full power of the radiated the antenna concentrate the main lobe concentrate the whole maximum power in it, and that half power beam width tell us that how the half of the power is spreaded by the antenna in the direction, in the radiated direction basically. So the angular separation between 3 dB down points on the field strength of the radiation pattern, it is called the half power beam width, and it is expressed in degrees. Basically there can be 120 degree. The separation between these 2 points where the power is half of the radiation, if that angle of the separation of these points are less, so we can say this is unidirectional antenna and this is fan beam antenna, pencil beam antenna, other kind of antennas. So that now here the gain and directivity, especially the antenna gain or power gain of an antenna is defined as the ratio of the intensity radiated by the antenna in the direction of its maximum output at an arbitrary distance divided by the intensity radiated at the same distance by a hypothetical isotropic antenna. This is the one definition. The other definition can be that antenna radiated, that the radiated power of antenna, we can divide the power accepted by the antenna, and it is radiated isotropically. Okay, and the directivity here we can see a function of direction is defined by the ratio of the radiation intensity of an antenna in direction of the main radiation intensity in all directions. So we can relate gain and directivity with the efficiency here, that the gain is equals to efficiency multiplied by directivity. Okay, so the efficiency is basically the radiation efficiency of the antenna is the ratio of power radiated to the power accepted by the antenna. So that is why this is the multiplication of the directivity. This is the multiplication factor of the directivity to express the gain, because input power is related here. Now the second definition is the efficiency of a transmitter antenna is the ratio of power actually radiated to the power absorbed by the antenna terminals. Now the third one is bandwidth. As we know, the bandwidth is the separation of the frequency points where the antenna we can operate. Sometimes we can see here that to define the bandwidth, there we have certain parameters that we can say VSWR and the reflection coefficients or the return loss. So if the bandwidth of an antenna expressed in its ability to separate over a wide frequency range, it is often defined as the range over which the power gain is maintained to within 3 dB of its maximum value, or the range over which the VSWR is no longer no greater than 2:1 ratio, whichever is smaller, the bandwidth is usually given as percentage of the nominal operating frequency. The radiation pattern of an antenna may change dramatically outside its specified operating bandwidth. So other than that, we can define if the return loss is minus 10 dB, which is equal to that 2 dB VSWR equals to 2. So we can define the bandwidth both with both the parameters, the VSWR as well as return loss. So the polarization. The next parameter is polarization, where the polarization is very important parameter here. That where we can establish a communication link between two antennas if the orientation of antenna is not matched with the transmitted one. Okay, what I mean to say that if the receiving antenna is not oriented with the uh, transmitting antenna, so that maximum reception will not happen. Okay, so that we can see theoretically here that the polarization of an antenna is the orientation of electrical field of the electric field of the radio wave with respect to the earth's surface, and it determined by the physical structure of the antenna and by its orientation. A simple straight wire antenna will have one polarization when the mounted vertically and a different polarization when mounted horizontally. So if the dipole which is vertical respected to the ground and other one is the horizontal with respect to ground, so the reception or the communication link will not establish if the orientation is not the same. Okay, so the reflections generally affects polarization for radio wave. The most important reflectors is the ionosphere. Signals which reflects from it will have their polarization changed, and definitely after the reflection the polarization will definitely change. So we arrange our receiver antenna according to that. Okay, so so other than that we have three kind of polarization, that they are a linear polarization, elliptical polarization and the circular polarization of the wave. If the wave is circularly polarized, so there are two separate polarization where we can say that right hand circularly polarized and polarization and the left hand circularly polarization. I will tell you later. So now that here that we can see several structures. So these are basically types of antenna. So in the first one there are wire antenna. So wire antenna has its own kind, that dipole antenna and the loop antenna, and this is hello. Am I audible?
Yes, sir, you are audible.
सुनाई दे रहा है? Okay. So this is the wire antenna, and other antenna is the aperture antenna, where we can use the waveguide, and the array antennas. Array antenna is nothing but the array of the single unit of the antenna, and the reflector antenna is we place here the reflector in front of the main antenna. So, so the antenna link can be established here. That a lens antenna, that we place a lens in front of the main antenna where that wave is propagate in the direction, in the single direction. And here the sixth one is microstrip patch antenna, or we can sometimes we call it planar antenna. And here we can see there are several designs of the patch antenna. It can be square, rectangular, dipole, circular, elliptical, triangular, and dissection and ring section, and in the R section. In these designs, these designs are not limited. So we can place any design whatever we need for the uh, for the antenna design. So basically, that antenna designer can think any design to place uh, the antenna in the device where the area of the aperture, that the area of aperture is available. Other than that, we have a planar antenna, which is a spiral antenna. I will tell you that why I am that basically the today's topic is the spiral antenna. So I will tell you that before uh, to introduce the spiral antenna, I will tell you about the patch antenna here. So what is the patch antenna? Patch antenna basically that microstrip patch antenna was invented by the Bob Munson in 1972, and the microstrip antenna are attractive due to their lightweight, conformability, and low cost. And these antennas can be integrated in printed strip line, feed networks, and active devices. This is a relatively new area of antenna engineering. The radiation properties of the microstrip structure have been known since 1950. So, the resonance frequency of this antenna, that microstrip antenna, is related to the length of the antenna basically, and it is not related to the width of the antenna. It is related to the majorly it is related to the length of the antenna. So that here we can see that I have written here F10. So this is the dominant mode where the length is related to the mode. Okay. So that one is that half wavelength is related to the L, the length of the antenna. Okay. So okay. Now the second thing is that antenna length or dimension is also related to the relative dielectric constant of the substrate also. If the substrate, see, the frequency is reciprocal to the substrate. So if the dielectric constant increased here, so the frequency or the dominant frequency or the operating frequency will decrease. Okay. The patch antenna applications, I have written here that there are several basically that we use recently, or in today's communication devices, all devices has the patch antenna only. So that I have written some application here that patch antenna can be used in satellite communication, microwave communication, cell phone antennas, and GPS antennas. Okay. So the patch antenna advantages and disadvantages are that it is lightweight and low volume, easy to fabricate, easy to feed, and there are several feeding techniques to feed the antenna. Mainly we use the coaxial cable to feed it and the microstrip line to feed it. And it is easy to use in an array or incorporate with other microstrip circuit elements. Like we can fix our antenna or we can make our antenna in a PCB PCB board that we don't want to make separate antenna if it is not necessary. So we can print our antenna on the PCB only. Okay, so it is very feasible antenna actually. So and it is mechanically robust and when mounted on a rigid surface, and it is mechanically stable antenna. The disadvantages of this antenna definitely that some disadvantages it has. It is narrow bandwidth and the efficiency is very low and the gain is very low and the radiation from the feed and junctions it comes from the radiation comes from the feed and the junctions where we fix the microstrip antenna. The low power handling capacity, because if we put the high power uh, uh, to the antenna, if we feed this antenna with high power, so it may be burned because it is the microstrip antenna mounted over a dielectric material, and it is not thermally stable. So the conductor and dielectric losses are more severe on thinner substrates. Okay, if the substrate is thin, so we cannot that losses will increase. A surface wave losses becomes more severe for thicker substrate. Okay, so these are the advantages and disadvantages of the patch antenna. So the performance. So because of the disadvantages, the antenna engineers want to overcome these disadvantages. So that antenna designers invented some techniques to improve the performance of the antenna. So I have that there are, so here there are some very popular techniques to improve the performance of the antenna, and these are metamaterials and EBG basically. So we can see that by using metamaterial in antenna, we can change the gain, directivity, size, efficiency, and bandwidth. See, the metamaterial is able to change the or to alter the gain, directivity, size, efficiency, and bandwidth. So it is very important technique to improve the performance of the antenna. So the metamaterial mainly used to improve the radiation pattern and in matching property of the antenna. And the second technique is that EBG structures have inherent property of guiding and controlling the EM waves propagation and surface wave suppression, which improve the performance by reducing back radiation. So in the microstrip patch antenna, if we don't use the proper dimension of the ground plane, so the back lobe will increase. So to minimize the size of the antenna, we we use EBG structure to suppress the surface wave. Okay, so there are so here the metamaterials. Metamaterial is basically that, as I have written here, the meta. The meta word is a Greek word which means sometimes beyond and alter and or change. So what it is, the metamaterial basically materials that have their electromagnetic properties altered to something beyond what cannot be found in nature. So that metamaterial is not possible in the nature. In nature, what I mean to say that the material that we find in the nature, that the materials are not the metamaterial, that there are two properties, epsilon and mu, of the material, that electrical properties that we use to design antenna. So in nature we find positive mu and epsilon. So to design a metamaterial, we alter these properties in a such a way that it should be in negative in nature. Okay, so here it's a graph that where we can identify what is the metamaterial actually is. So the electrical permittivity and the magnetic permeability are the main determinant of a material response to electromagnetic waves. In metamaterials, both these material parameters are negative. Okay, as I already told you that we have epsilon and mu. So we find the double positive material in nature, natural isotropic dielectrics. Okay, so these two properties which are related to the designing of antenna, or electrical property basically which we can use to design an antenna. So if it is negative, suppose if epsilon is negative, so here we come here at the second quadrant where the plasma is introduced, the metal at optical frequencies. Okay, or we can find, or we can make this negative epsilon with the help of thin wire mesh structure. Okay, so this is epsilon negative materials. And in the fourth quadrant we have mu negative material, where that mu is negative, and we can say these are ferrites. Okay, so we can make these ferrites or artificial ferrites with the help of SRR. Okay, so split ring resonator, basically SRR is stand for the split ring resonators. So that we can make artificial ferrite with the help of SRR. And in the third quadrant, where we can see the double negative material. So the double negative material is not possible and no natural occurrence. As I told you that no natural occurrence, because that sometimes the mu is negative but the epsilon is positive, and epsilon is positive but mu is negative, you can find, but both the parameters are negative, we don't find in the nature. So it is These materials are metamaterials, and we call it negative index material or double negative materials. So these were the metamaterials, and second one is electromagnetic band gap structures. So band gap structure, basically the EBG structure have been investigated for the improving performance of numerous RF and micro devices utilize the surface wave suppression and the artificial magnetic conductors. Properties of these special type metamaterials. We can make metamaterial, or we can use the metamaterial as an if we alter the property, or if we alter the position of the metamaterial, or when we put the metamaterial over the dielectric, so the uh, property can be evaluated as an EBG structure. Okay, so the different EBG structures are 3, 2, and 1 dimensional. That can be mushroom, uniplanar EBG, and their successive advancement. Like I have shown here that 1D EBG and 2D EBG and 3D EBG. Okay, so that 1D EBG is like this is the strip line, and beneath this that we have circular holes in the ground that can resist the propagation of the surface waves. Okay, so this is one dimensional EBG, and the second one is the cross view of, you can see that EBG is in the XY plane, and it is spread over the uh, ground plane of the antenna. So we can see it is 2D, and the 3D EBG structure is we spread these components, that unit cells, in 3 dimension. It has length, width, and height also. Okay, now that antenna design needs some analysis and some efforts to design the proper antenna, or that antenna we use for the system. So the workflow of the antenna and designing I have shown here, that we can see the analytical formulas which we can have in our references. So initially, dimension, principle, or idea we can take from the handbook or papers, and the second one is 3D modeling or simulation of the antenna. So we use this software, or any software, any platform to design it. Now, initially, suppose that if I replace this screen portion in this workflow, what will happen? What will happen here? See, if I eliminate this screen portion, the 3D simulation softwares, what will happen here? That we will have the analytical formula and the fabrication technology. So that after the analytical formula, we direct go to the fabrication technology, and what will happen, that it will increase the cost of the fabrication, because that from the single attempt, we that no one able to design perfect antenna. Okay, so there are several. It was a hit and trial method to design a perfect antenna. So it was not cost effective. So to reduce the cost of the fabrication, that engineers introduced the 3D simulation design, where the simulation we can have the simulation initially according to the design formulas, and we relate these simulations to the real time, that so the cost will reduce, and cost it definitely is it reduced, so that we use CST or HFSS and i3D other softwares to design antenna or microwave components. Okay, so here the third one is fabrication technology. So here I have shown that this is very time-taking and expensive process, and I have shown one machine here to print or to design or to fabricate antenna. Now after that, the measurement will happen at the VNA and other measurement devices. So at the one here, one important factor here is I have to mention that if that measurement and the simulation is not matched, so we will go again to the simulation process to finalize the antenna or to optimize the antenna. Okay, so that is the whole workflow of the antenna designing or any micro component design right now. So, so these were the introduction. That were the introduction, and right now uh, I want to show that initial patch antenna design that I have made. So here, that as I told you that the performance improvement of the planar antenna. So how can we improve the performance of the antenna? We can see this is the basic patch antenna, and this patch antenna has a feeding line. Okay, this is the 50 ohm transmission, 50 ohm microstrip line, and this is the quarter wave microstrip line. So the simple patch antenna, the performance of the simple patch antenna, we can see in the black one, the minus 10 dB, as I told you that this is the reflection coefficient, and we can see if there is not if I mention in the positive manner, so it will be a return loss. Okay, so here we can see that minus 10 dB, that if it is simple patch antenna, so the performance is very weak, or it is narrow band. After the attachment of these spirals or curls to the non-radiating edges, so the performance of the antenna improves dramatically. So what will happen here? That basically these circles, these curls reduce the surface weight and improve the performance of the antenna. So with the simple technique, with simple technique and just attachment of these curls, we can improve the performance of the antenna here. So that we can see that antenna, the narrowband antenna, it converts into the broadband antenna. Okay, so the bandwidth enhancement is achieved by impedance matching in the operating range. Okay, so see, there are some input impedance parameters, and we improve in a broadband manner. Okay, so to reduce or to improve the bandwidth, we need to find that impedance, the real impedance of the antenna should be in 50 or 75 ohm, and the reactive component of the impedance should be near about 0. Okay, so after the attachment of these curls, we have find or we achieve the 0 reactive component. Yeah. So this is the pictorial view where the excitation of the antenna happens, and according to the excitation, that radiation pattern occurs. So that we can see that initially in simple patch antenna, we have excitation like this, where the blue is the negative cycle and the positive is the red one is the positive cycle. And after the excitation we can see here the radiation pattern is unidirectional, because that patch antenna has the ground plane, and the ground plane is metallic, so it will reflect from the one direction, and so we achieve this portion or this way, this radiation pattern in a single direction. And the gain, we can see the gain is 4.97. Okay, after the attachment of ABCD curls, so that intensity of the excitation is improved, and then we have find that we have found the gain is improved, that which is previously that we have 5 dB, and here it is 7 dB. So the efficiency is also improved and gain is also improved in the operating frequency. Okay, so this is the simple technique to improve the performance of an antenna. Okay, we can use other techniques, and that was a simple and easy technique used by me. See, and this is a simple comparison of the parameters of the antenna, of the fabricated antenna. Let's see that that antenna is fabricated, and the performance of the antenna in the comparison of measured and simulated, that measured and simulated antenna shows almost similar results. And here the bandwidth of the simple patch antenna was 6%, and here that design antenna was 14%, and the gain was 5, and the design antenna has gain of 7 dB. Directivity was 7, and the design antenna has that 9 dB. Radiation efficiency is also improved. The total efficiency is also improved. So this was the first approach to improve performance of an antenna. You can use other techniques like U slot or other uh, like U slot or cull improvement or like uh, metamaterial or EBG and race predictive impedance surfaces. So there are several techniques to improve performance of patch antenna. Okay, so let's see that was the patch antenna, and that was simple patch antenna. So now come to the spiral antenna, which is a type of patch antenna, and it has some uh, properties that we can select this spiral antenna for several applications. So what are the properties? Hmm, let's see. So why spiral antenna? The spiral antenna, the features of the spiral antenna is it has large bandwidth, wide beam width, circularly polarized, and polarization independent on receiving mode, and fabrication is very easy. And the important application, electron. See the electronic countermeasure. What is electronic countermeasure is the countermeasure is like if you want to measure frequency or if you want to judge frequency in the free space, so you need to have an antenna which is frequency independent, so you can receive any signal from anywhere. Okay, so that spiral antenna is basically a frequency independent antenna, and you can use it for countermeasure application. And it is the very important application in the battlefield, basically, where we can identify that frequency bands of enemy. So second one is radar application, and we can use airborne application. The airborne application, that if you use the antenna at the surface of plane or any other aircraft, so that the plane is not oriented in a single direction. So uh, you need to design an antenna which is oriented independent antenna. Okay, so the spiral antenna is the most suitable candidate where we can use. And navigations, definitely that orientation here in the same manner. Spiral antenna is can be used in the navigation also in satellite communications. So uh, that I as I told you that spiral antenna is the frequency independent antenna. So uh, see that why we call it planar antenna. So inspired from the planar kind of antenna structures, generally they are narrow band structures, but spiral has its own merits over other antenna. So what it is that most common configurations are Archimedean spiral and equilateral spiral. Before we discuss these antennas, I want to uh, differ this patch antenna from the spiral antenna. What it is that patch antenna is narrow bandwidth and efficiency was low, and the it has uh, low bandwidth. So other that benefit over the patch antenna, spiral antenna has a wide bandwidth and high gain, and it is circularly polarized. So with uh, the same thing I have mentioned here, that spiral antenna is circularly polarized radiator and consistent input impedance. That input impedance, when we talk about the input impedance, that input impedance is related to the input which we are taken from the transmission line for antenna. That is, obviously it is 50 or 750 ohm, and sometimes it is 75 ohm. But at the surface of the antenna, at the feeding point of the antenna, or at the edge of the antenna, that impedance is not 75 ohm or not 50 ohm. So it is related to, or it is equal to 180 or 188 or 200 ohm. So that input impedance of the patch antenna is not consistent. As we increase the dimension of the patch, that the impedance increase. I mean gradually if we increase the dimension of the antenna, of dimension of the patch antenna. So, but in case of spiral antenna, it is consistent. Means it, if it is consistent in the frequency range, so, and similarly it consistent in the input impedance range. However, the input impedance is very high for the spiral antenna, because spiral antenna is self-complementary antenna. And if you have heard about the Wegener's principle, so that the metallic portion and the slotted portion input impedance, if we multiply both of them, so it will be equal to eta square by 4, and the eta is 377 ohm and free space or free space characteristic impedance. So if we do calculation with with respect of self complementary antenna, so it will comes 188 ohm. Okay, so consistent radiation pattern over wide frequency range. Similarly, that if the impedance, if consistent input impedance we have in the Archimedean spiral, so we will have the consistent frequency range. Okay, so there are some advantages and drawbacks. Definitely, it has drawbacks also. The advantages are wide bandwidth, consistent gain over wide band, wide beam width, circularly polarized, and polarization independent over receiving mode and easy fabrication. Drawbacks are large in size and bidirectional radiation, high input impedance, and balloon needed for feeding. The balloon means the balance line we need to feed it, because as I told you that general transmission lines have the input impedance 50 ohm, but as I told you that spiral antenna has the input impedance 188 ohm, so we cannot match it. So we cannot directly feed it. Okay, so we need balloon, which is valence line transformer. So we use balloon to match the input impedance from transmission line to the spiral antenna. Okay, so see, uh, so here I have shown some literature to introduce that literature related to the spiral antenna. The spiral antenna that these researchers have made, that the spiral antenna was introduced in 1960 by Keyser, and they have made uh, a array of it, and they just made that spiral antenna and just made it unidirectional with the help of the reflector. Okay, and similarly, that after the evolution of this design, there are several engineers have put their effort to improve have put their effort to improve the performance of the antenna or spiral antenna. So see, there is a dielectric plate over spiral antenna, and here we have used the ABG structures, and here we have absorber or cavity to improve the performance of antenna, and there are several other techniques to improve the performance of the spiral antenna. So that as I told you, that miniaturization of the antenna of spiral antenna was very important, and I have made this with the help of stacked ring. See that I have designed this balloon and put a ring beneath the antenna structure, so that antenna dimension is reduced, and I have found the ring established the matching of the impedance also. So what happens here, see, initially, initially that simple spiral was D at black one. At the black one, we have 3 gigahertz. Then after the attachment of the ring, we got it and we shift this frequency at the 2 gigahertz. So this is the miniaturization techniques, the simple miniaturization techniques I have used here, and that without alteration of its property. So the property of the spiral antenna is very important. So it is very hard, or it is very difficult to uh, attach something to the spiral antenna without alteration of properties of spiral antenna. So it is very important to preserve the spiral antenna properties. So I have made it. In here I have shown a simple comparison with the stacked ring spiral antenna, that SRSA, and I have compared with the two. I have compared with two works here. That is, so with the help of stacked ring, I have made it and the miniaturized antenna 42%. Here we can see the initial and lowest frequency before modification, that was 2.64 gigahertz. After the attachment or modification, that was the 2.5 gigahertz. The frequency difference was 599 megahertz, 590 megahertz, and the radius and miniaturized area is 42%. Okay, and that antenna properties was I was able to uh, uh, I preserved that antenna characteristic to when I attach the stacked ring. Okay, so this is the result. These are the result, basically simulated one and the measured one, and both are in agreement. Now that after the miniaturization of the antenna, spiral antenna, I worked on the gain enhancement of the antenna. See that, as I already told you, that spiral antenna is a frequency independent antenna, and we cannot lose the characteristic of it. So it is very difficult to improve gain of the antenna in the whole bandwidth, because that metamaterial and ABZ was the frequency dependent uh, structures, and it is very the both uh, structures like metamaterial or ABZ are very narrow band structures, and we cannot use it in uh, in spiral kind of antennas, because two properties are there. The first is it is very wideband or frequency independent, or second thing is it is circularly polarized. So sometimes we use the parallel metamaterial to improve the circularly polarized antenna, but we use them at narrow band. Okay, but what I have done here, we I have used a simple plate of dielectric, which is easily available in the market, that is FR4. Now, what I found, that if I place the dielectric plate on antenna, so that property of the antenna improve dramatically. Okay, so we can see that if this last work is I have made this cross slab, and that antenna, see the gain of the antenna. I want to show you this structure first. That initially uh, I put a plate on it, on the spiral antenna, but in this structure I have put a slab, a cross slab over the spiral antenna. Then it improved it improves the directivity of the antenna dramatically, because that we can see that Archimedean spiral antenna has the lowest gain at the high frequency. But if I place the dielectric slab, so that we can see that directivity of the antenna is improved. Okay, and the axle ratio is maintained, and that radiation efficiency is maintained, and other parameters are maintained. So we can see, so this is the pattern, and this is, see, the electric field distribution and the radiation pattern I have mentioned, that we can see that before that there is I have select three frequencies: 6 gigahertz, 9 gigahertz, and 12 gigahertz, and that Archimedean spiral antenna and the Swasa, that is Archimedean spiral antenna with cross slab, that stacked dielectric slab, and then I can show you here that here at the 12 gigahertz we don't have the concentrated electric field, but after the attachment of the slab we have the concentrated electric field. So that relative dielectric constant of the slab act as lens, that we can able to concentrate that whole electric field in a one direction. Okay, thank you. Any question, queries?
Dear participant, any question, any query, you can ask directly or you can type in the chat box. I think, sir, there is no question from participants. Sir, I have one question. So, I just want to know how to reduce simulation time in HFSS for antenna design, sir.
You can improve the mesh shells. Okay, you can reduce the mesh shells first if you want to reduce the time. Okay, first in the first simulation you can reduce the cell size, cell size, and then second one is you can reduce the aperture of the antenna. Are you getting my point?
Yes, sir. Thank you. Sir, one more question is there. There is any method to find out how much power an antenna can handle?
How much power antenna can handle? Yes, there is a procedure. There is a thermal stability procedure we have.
Okay.
Okay. So in that we feed the antenna throughout the day or throughout month, means it handle the power. Suppose we design an antenna. We design an antenna for 20 watt, or generally we design an antenna for 12 watt. Okay. Hello.
Okay, sir. Thank you. Thank you. Any other question from participants?
Yes.
Yes, sir. Do you want to say something?
Yes. Actually, if we want to design, if we design an antenna for 12 gigahertz, 12 watt, so if we make it for the higher power, so we need to stabilize that antenna, or we need to change the material. Okay.
Okay. Thank you.
Both the options we have, and we can put that antenna for the thermal stability procedure. So we can make it. We can make it for. We can test it for the thermal property. Okay.
Okay. Okay. Thank you very much, sir. Any other question from participants? Arya, if anyone have any doubt related to this spiral designing, antenna designing, you can ask now. Otherwise, we are going to end this session. Okay, I think, sir, there is no doubt. We don't have any queries from the participants. So thank you very much. I would like to thank you, and we look forward other sessions like this in other STCs also. And we are really thankful that you have taken out some this precious time for this short-term course. And have a good day, sir.
Thank you, Manju sir. Thank you.
So, dear participants, we will meet again at 2:30 for the next session for today. So, thank you very much and have a good day.
Thank you, participants.